It seems like our solar system breaks into two really distinct categories. There's what we call the terrestrial planets on the left-hand side here, the really small rocky planets like the Earth. And then there's these enormous gas giants, which are just truly giant compared to the size of Earth. What we want to try to understand is how did these planets get so big? Why are they so big? Particularly Jupiter and Saturn. Just, what caused them to grow so incredibly large? The idea here has to do with physics and maybe a little bit of chemistry, and I won't get into too much of the details, but I think we can understand it with a couple helpful visuals. So almost the entirety of the size of these outer planets is gas, right? It's not solid surface. It's chemical elements in the form of gas, right? They're not liquid, they're not solid, they're gas. And we need to understand a little bit about what causes gas to stay near something. We call it gas retention, keeping gas tied to you. Now what's pulling the gas in is gravity. Gravity's what's pulling and holding the gas there. What's pushing the gas away, why gas might want to leave, is heat and temperature. Now, just with that information, you're getting a sense of what's happening, right? Where it's warmer here at the inside planets, which are closer to the sun, there's more heat energy, and so it's harder for them to keep the gas. Further away, it's easier for them to keep the gas. So let's try to understand that. I have this little fictional chamber here, and to it I can add, let's just add some oxygen. Okay, so there's a bunch of oxygen particles in here, and anytime you have a whole bunch of particles, like chemical elements or whatever it might be, atoms, or even billiard balls, if they're bouncing around, they're going to have a distribution of speeds. Now again, this is kind of like high-level physics stuff, but we can understand it in the sense that there's a wide variety of speeds. Let me just set this thing in motion. Now you see the particles moving inside the box. Some of the particles, on average, will be moving faster than others. And this graph here shows the distribution of speeds of these particles. At any given moment, some particles will be moving really slow. We'll find one right there. Oop, he's going slow. But eventually, that little guy is going to get hit. Oh, and he's going to get going faster. So there's a random distribution of speeds. Sometimes people are slow, sometimes people are fast. But on average, you get this kind of distribution. All right, you get it. Now, gravity can hold on to things, but if something's moving really fast, it can actually escape. Right? So gravity's holding on to all these particles right now, but let's just say we have a limit to how much gravity there really is on a given planet. It's a small planet to begin with. All right, so I'm going to allow there to be some escape that can happen. All right, I have to stop it and then turn on allow escape. So now you can see the escape speed here. Now the escape speed will depend on how big the planet is, right? So if I have a smaller planet, it might be easier for particles to escape. It might escape at like 1,000 meters per second. So only the fastest particles will actually escape, right? So let me start the simulation now. And you'll see that the fast particles will start to leak out. You'll see maybe a couple that kind of sneak out of the box. Right? Oh, I lost a few. All right. Oh, there goes another one. All right, and so slowly, over time, I'm going to lose some of these particles. Right? And of course, the smaller the planet is to begin with, or the hotter the planet is, so let's just check this out, man. Let me stop it. If I turn the temperature way up, right, it gets hotter, 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 closer to the sun, that means more particles are going to escape, right, because they're moving faster. The warmer it is, the faster the particles move. And soon you can start to see I'm losing all this gas. It's leaving my planet. So I can't hold on to it. I'm not retaining it. Eventually, I'll lose all of it, or almost all of it. Okay, so what could happen? What allows me to keep an atmosphere? Well, I could be really cold. That would be one way to do it. All right, it could be really cold. Or I could have a ton of gravity. So if it's really, really cold, right, this distribution is going to mean only the fastest a particle can go might only be 500 meters per second. And if there's a ton of gravity, it means they have to have a really large escape speed. Okay, so for the outer planets, we see kind of both of these things sort of happening, right? One thing is that it's really, really cold out there. Another thing is as they started to get bigger, because they're holding on to this gas, it gets easier and easier for them to retain. The more stuff they have, the more that it can accumulate. Cool. Okay, so you get the idea of how this is working. Now, the other interesting piece is that different kinds of gases behave differently. So even at the same temperature and the same escape speed, if I add, let's say, hydrogen, bonk. All right, you can see hydrogen, the distribution of speeds that hydrogen would have, is very different than if I were to add, say, oxygen. Right, so the red line is hydrogen, the blue line's oxygen. So what does this mean? What it means is that certain gases are much harder to hold on to. Right? Hydrogen, for example, is really hard to hold on to. Oxygen is relatively easy to hold on to. Right? So what we see is that for our terrestrial planets, we've lost a lot of the hydrogen, a lot of the helium, because it's hard to hold on to. The outer planets have held on to way more of it because it's cooler out there, and it's easier for them to hold on to it because they have so much gravity. Now we're going to look at this one more way. I have one more sort of complicated graph to show you, okay, which is kind of interesting. We've just been seeing how the temperature of a planet could be different, right? It's hotter at the terrestrial planets by the sun, colder at the gas giants. We've also seen how the speed of the escape speed can be different depending on how much gravity you have. So if you have a lot of gravity, you have to go really fast to escape it. So if I show on this graph, I'd show where the gas giants are all up here. They're cold and they really have a lot of gravity, so they're hard to escape. The terrestrial planets, Mercury, Venus, Earth, and Mars, are down here. They're warmer and they're smaller, so they are a little, easier to escape. Now, I said that different gases, right, have different ways of being retained, and some are easier, some are harder. So I'm going to turn those gases on. You can check it out. So hydrogen, for example, is hard to hold on to. In other words, you have to have a lot of gravity or be really cold, and so the gas giants can hold on to it, but you'll notice that none of the terrestrial planets can hold on to their hydrogen. Helium's a lot the same way, right? And methane, a little more so. So the Earth and Venus have been able to hold on to more methane in their atmosphere. But as a percentage of our atmosphere, we have a lot more of things like water, nitrogen, oxygen, and carbon dioxide. But you'll see that some planets still are too hot and too small to even keep those kind of atmospheres. So you see Mercury right here still doesn't really have any sort of atmosphere because it's still too hot and too small. Now I want to point out one item in particular, and that is water, because this will play into some of our later discussions. There's a line here between which water can exist in an atmosphere or water escapes. Now you'll see that Mercury definitely doesn't have any water in its atmosphere, because it doesn't have any atmosphere. But Mars is just below the line, so it can't really hold on to the water either. Venus and Earth could, except Venus, because of the greenhouse effect, that's not taken into account in this graph, it's too hot, so it can't really hold on to it either. Alright, so this has been a little high level to show you kind of some of the physics, but I hope it illustrates the point of why these gas giants are so much bigger than the terrestrial planets. They're just better at holding on to gas than the Earth is.